Hello students, so in our previous lecture we have that is lecture number 177, the concept of quantum capacitance was introduced, and that whenever we are having a metal and molecule contact, a slight change in the charges of there's a charge transfer taking place, then it will lead to a change in the Fermi level, and it will be given as equal to the change in charge transfer divided by the density of states, and it can be further quantified by this quantum capacitance given as Cu. So we can write Cu as equal to Q square G, and so ultimately this change in Fermi level is equal to Q square by Cu into delta n. This was explained in my previous lecture, that is lecture number 177. Now, this quantum capacitance, if in a metallic contact, there are a large number of density of states. At the Fermi level. So a large number of density of state implies that a large number of charges transfer should take place to cause any change in the Fermi level. So we can see that if the number of density of states is large, so it's very difficult. It's comparatively difficult to change the Fermi level. So we can imply it is pinned. The Fermi level is pinned by the large number of density of states. So the quantum capacitance can be employed in an equivalent circuit for the metal molecular junction, but we have to generalize the circuit such that each node potential is Fermi level, not just electrostatic potential as in the conventional electrostatic circuit. So in the divider we form a circuit which is somewhat given as it is a metal Me is a circuit with resistance R, and this is the molecule. The equivalent circuit, and we define it by TF0, and this is the capacitance, and this is the EF. This is the equivalent circuit. So in this equivalent circuit, the metal gets modeled by a very source, a voltage source. And the voltage source is equal to the chemical potential of the metal. before the contact has taken place, before the metal has been contacted with the molecule, the molecule from level was EF 0, and after the contact has taken place, the contact is modeled by a resistor that allows current to flow. So this is also after contact. The resistance R, which will allow the current flow. And this will be active when this Fermi level on other side are misaligned. It will cause the current to flow to make the alignment. Now, when there is a charge flowing, it flows from the metal to the molecule. It develops a potential across the quantum capacitance. Across the quantum capacitance. But as the Fermi as we have already seen that the quantum capacitance is given as is equal to q square GeF, so it will always depend upon the Fermi level of the molecule. Now, it's very, so we know that U is equal to q square EF. So q square is dependent upon EF, and there is only an exception if the density of states is constant. Only then this U will be independent of this Fermi level. So we can say that we can have a constant quantum capacitance C0. If there are small deviations between, only if there are small deviations between the chemical potential, that is mu I, and the initial Fermi level of the molecule. Only then I can achieve a constant quantum capacitance. Now, apart from quantum capacitance, this is C0, we will have electrostatic capacitance, which is called CES. This is the electrostatic capacitance. CES. Now, we have previously explained the contact between a molecule, between a metal and a molecule by a water tank model. But however, what we have to understand that it is the flow of electrons that is taking place, and electrons are quite different from water because the electrons are charged. So whenever an electron is transferring from, say, the metal to the molecule, it is leaving behind a hole or a positively charged, and also there is a net negative charge built up at the molecular side. So any charging at the interface it changes the potential of the molecule relative to the metal. Now, as say as charging as the electronic charge is taking place, so what it will do, it will reduce the number of electrons that are transferred after the contact is made. So it will cause a reduction in delta n after the charge is made, after the contact has been made. So if taking again the water tank models, if this is the initial condition, so the Fermi level of the metal, and say this was the Fermi level of the molecule. So what is happening that as the electron is flowing from the metal to molecule, the Fermi level is shooting up, and we are having a Fermi level here. And this is non-equilibrium case. And whenever the equilibrium is achieved, automatically, we have seen it earlier that there is a shift in the Fermi level. As we have seen that instead of water, they are taking electron, since they carry charge, they shift the potential when they are transferred. So it is similar to what is actually happening. So whenever there is a shift in charge, change in potential is taking place, and it is equivalent to lifting of the molecular Fermi level. Now, what is important here is that this contact, this can be considered as the two plates of a capacitor. So whenever there is a charge transfer, the capacitor is charged and a voltage is established, and the molecular changes potential. So the change in the molecular potential per electron transfer is known as the charging density, and is reflected in the vacuum energy. Now, so we can express this capacitance. This is actually the electrostatic capacitance that we actually talked about. That is equal to Q by V, charge transferred by the voltage established. So V is the voltage across the capacitor, and C is the electrostatic charge, and Q is the charge transfer. Now the change in potential due to charging. It can be expressed as UE V is equal to QE is equal to Q square by CS into delta N. So it's actually like this. You have a contact here, and you have a molecule here. And this is the voltage. So this is how the charge transfer is taking place from the contact molecule into the latch. The capacitance is being developed. The voltage VL load voltage. So the contact in a molecule can be modeled by two plates of a parallel plate capacitor, and when the charge is transferred, that is when this Q is taking place, the electrostatic capacitor determines the charge in the electrostatic potential and the shift in the vacuum energy. So it also causes the shift in the vacuum energy. And the total voltage VC is equal to total voltage V is equal to VC plus Q by CES.